Hello. Welcome. Welcome. So, here we are at a blank page. And it can be a little bit tempting to just rush ahead and start doing things, implement what you know how to implement, but let's not get ahead of ourselves here. So the first few episodes, I think I'll just have a bit of a tutorial on, you know, what's going on here. I'm hoping that'll help once I get to some of the more advanced stuff and I'm doing more of a devlog format where I'm just showing progress. So let's get into this program. We have a bunch of different things in these menus here. Most of the components are hidden away in the components menu item here. We've got some logic. We have input output. So we've got input pins and output pins here. We've got wires. This is more like, various miscellaneous wire related things. We have plexers, or we have multiplexers and demultiplexers. We have flip-flops, which we can use for registers. Registers are just, you can think of them as variables, if you're familiar with that term. It's just a place to store a number, essentially. Either just a Boolean, a true false value, or an arbitrary integer. And for that matter, the wires in this program are that way as well. So let's tinker with that a little bit. So this is a simple circuit. This is the supply rail, or the positive voltage, and this is the ground rail, or the negative voltage. And you can probably imagine what this will do. Oh, we got a short circuit. So, and it highlights the wire in red when that happens. So let's try something else. Let's have an input and an output. So in this case, we can turn this on and it turns this one on. We can turn it off and it turns this one off. So in this case, this wire only has a single bit in it, and that bit is either 1 or 0. But we can change it to 32 bits, for example, and we can give it a name as well. And we can change this one to 32 bits, and we can give it a name. So we can turn on multiple bits, and it will send all of those bits over what appears to be a single wire. But you can think of this wire as a bus, or 32 parallel wires. It's just a simplification so that you don't have to have 32 individual wires going between components. You can have them all bundled into a single wire. So you can think of a wire as either, I'm trying to think of like various different ways that I know how to refer to this concept. If you're familiar with programming terms, you can think of a wire as either a Boolean when it's a single bit, or an integer when it's an arbitrary number of bits, or more like it can carry an integer on the wire, if that makes sense. What else do we got in here? We also have some arithmetic. So the simplest possible thing that we could do to move towards having an actual CPU is to add two numbers together. So what I did there is I just copy pasted it. So you can select something and then copy, just Control C, Control V. And then I think I need to make, well, let's see what the error is. So this is a common error that you'll get. 32 bits needed, but 1 bit's found. And it'll highlight something. Usually it's somewhat close to where the problem is. Sometimes it can take a little while to find the problem. And then here's another error. This one says open inputs are not allowed. So it's circling the component that has the problem, and it says an input is open, which is another way of saying like dangling or not connected. There's a few ways to fix it. We could assign a constant value. We could say this value is 0 and wire that up. That's one way, and it does work. The other way that we can do it is we can use since it's a single bit, we can just use the ground. And that also works. So ground is 0 and the supply is 1. So actually we could show that. With R you can rotate. So now I've sent the supply voltage into the carry in bit, and you can see now we're getting 1 when the inputs are 0. That is that. Let's change it back to ground. So we can add numbers. Let's add 100 and let's add 54. And you see it somewhat unhelpfully converted those into hexadecimal for us, and then now this output is kind of gibberish. We have no idea if it worked properly. So let's fix that. In the advanced here, you can specify the default number format. So we can set it to sign decimal. And we can do the same for the inputs here. All right. So now it defaults to decimal over here. So we have 100 and the output is 100. That's a lot easier to tell that it's doing the right thing. And we have 54 here, and we have 154 here. So yeah, it's definitely adding 2 numbers. Awesome. What we could do is try doing some encoding of instructions. So this here is a splitter. What it'll do is it'll take a set of input wires or buses and produce a set of output wires or buses. And you can use this to change around bits. So if you go into the help in here, there's quite a bit of information in here. I'll let you read it, but it basically explains how to configure this thing. You've got a variety of different ways of specifying the bits, both on the input and the output. In this case, we've got an instruction, and let's just say that our instructions are 32 bits for now. And let's just say that our only instruction is the add instruction, and it adds 2 16 bits, numbers that have been packed into the instruction itself. So, but it's not super human friendly as it is. So let's do this, and let's flip this around. So then we can encode an instruction. The instruction can go over this wire. These inputs now become 16 bits. And this needs to become 16 bits. And now our output is 16 bits as well. Okay. Well, that works. Yep, it's the same, other than our numbers are now half the size, but that's okay. So we're encoding some instructions. One of the basic things that you would want to do in this program is you would want to have embedded circuits so that you can do more of a hierarchical design. So in order to do that, we need to go in here and do new embedded circuit. File, save as. Let's call this the decoder, since we just built a decoder. In here we'll need some inputs and we'll need some outputs. We want to copy and paste a part of the circuit that we built. So let's just grab this. If you click somewhere and you need to get out of it, just press escape. Okay, so we have the decoder part of the circuit. We can wire that up. All right, and then we can test this circuit independently if we run it. So that makes it quite nice for testing. So let's see, we've got some arbitrary bits up here and we've got some arbitrary bits down here, and you can see that it's splitting properly. And it'll give you errors if anything's wrong, so I always hit the play. So let's save this, and I always go in here and change the circuit specific settings because I don't like the defaults. Defaults are this yellow color, and I'm sorry for all of the yellow fans. I know there's many of you out there. I am not one of them. So I always change it to blue because I like blue. So label, this is our decoder. Okay, so we have a decoder. Let's use it. So in here, you can see there's a custom component, and that custom component can be a decoder. So now you can see what it looks like. And if you need to get back into the circuit itself, you can open the circuit here and it'll bring it back up. Okay, so let's replace the part of this circuit that is the decoder. And it should work the same, but let's just make sure that that's the case. And it indeed does. So that's how you would make deeper levels or higher levels of abstraction. You can kind of think of these as functions in a programming language. You have functions that do common tasks, and sometimes not even common. Maybe it's only called once in the entire program, but it removes a bunch of details that you don't really need to know at the higher level, and it just makes it easier to reason about what you're building at a higher level. You can more easily see what parts are connected to what, and it kind of gives you more of a block diagram view. Well, same thing in circuits. You would do that just to keep the higher level parts of the circuit manageable as far as complexity and crazy amounts of detail. Let's put the execution unit in its own circuit as well. New embedded circuit. So we can also test it here, make sure that it's working. These will default to hex. So let's just fix that. Okay, let's just test that. All right, and we have our result. Let's just modify this. Okay, I think that's everything. So we now have a custom component for our execute. Let's replace this. And I'm not quite sure why when you have two inputs like this, it'll split them like that. There we go. I think this will still work. Yep. Okay. Well, I think that's pretty good for now. We have a very crude beginning of a processor that can only add numbers, and that's the only instruction it understands. I think this is a pretty good beginning. Thank you very much for watching. Have yourself a great day. Bye.